Hey guys, my name is Will Buchanan, and this is Lab 4 involving oscillations for Physics 2211. So a quick overview, the goals of this lab are to understand the motion of an oscillating spring, and we can do this by using the energy principles and Newton's second law to create a model that closely resembles the experimental model of an oscillating spring. And the results show us that the energy principles allow us to get very close to modeling an experimental oscillating spring. And it also shows us that the net energy change throughout the duration of the experiment will remain at zero because no outside work is done. So that proves to be true. And the setup includes the Earth, the weight, and the spring, and we consider no external surroundings. So some good concepts to understand include the momentum principle found here, the velocity update formula here, the position update formula, and the net force, which in this setup is just gravity versus the spring force. And here are the energy principles. And up here we see that the total change in energy can be found by summing all the types of energy present. And this ellipses is included because there are different kinds of energies that exist outside of these three, but these are the three key ones for this experiment. And these include translational kinetic energy, potential spring energy, and potential gravity energy. And down here, we'll see that the change in energy for our system will be zero again, because no work is done. So the computational model aims to model the oscillations of the recorded spring as close as possible. So we want our code to get as close as we can to the actual video of the weight being dropped from the spring. The first graph shown displays the energy levels in the computational models, and the second and third graph show the X and Y positions along the way. And let's take a quick look at Tracker, which is some software we use to gather the data points accurately for the experimental model. And these are the initial conditions found down here of the experiment. So taking a look at Auto Tracker, we can see it pinpoints exactly where that weight is throughout the time and gives us a nice data set down here. And it does it much quicker than if you were to do it by, say, hand or something. And then a look at the code. Here's some initial conditions, more initial conditions, and then the types of energy present can be found down here. And then this is our while loop, which actually performs the model. And we see the length of this and direction of the spring down here, and the different energy types, the kinetic energy with the same formula, the potential gravity and potential spring, and the summation of those energies right here. All right, let's run our code. So we see the spring oscillating and the weight moving. And then in this graph, we can see the potential energy of the spring in green, the potential energy of gravity in red, and the kinetic energy in blue. And notice that the total energy remains at zero because no external work is being done. So as long as this continues, these pretty much just oscillate back and forth and never really change in our computational model. And then along the x-axis, the period time of the oscillations, or from basically crest to crest, are like the same value over the span of the x-axis. And the computational model was 1.664 seconds, and the experimental is 1.647 seconds, which is very close. And in the y-axis, they're actually the same value. So we got very close to modeling the period times. However, if we look on our graphs, they're actually offset a little bit, and that's likely due to some issues with the initial conditions of the model versus the video. And I tried to plug in the same values, but they're still offset. However, the actual period lengths are from, say, like this point to this point and this point to this point are very close. And then another question is the energy principle satisfied? And the answer is yes, because the total energy never changes from zero. This is as expected, again, because no outside work is done. And although we see the different kinds of energy changing and going up and down throughout the graph, that orange line, which is the total energy, stays constant because no external work is being done. All right, that's it for my lab. Thanks for watching.